in New York.
Thank you, Thomas, and thanks everyone for coming on a Friday. So what we see here is an image of a tide gauge in New York on Governor's Island in the year 1890. And if you spend a lot of time in archives, as I have, you'll find some of these images, and they're very beautiful. What I'm trying to do today is do a similar thing for data from the 1800s and try to see a glimpse of what storm tides and tides were like in the 1800s in New York. So a few years ago, I was very persistent, and I went to the U.S. National Archives in Washington, D.C., and I discovered a number of old tide data from the 1800s, extensive data from all over, so from the West Coast, from the East Coast, altogether about 300 years of data that has not been analyzed in many cases in over 100 years. And today I'm going to focus on the New York area, in which is the longest continuous series going back to about 1844. So this is a picture of New York Harbor and of the different gauges that are there. You can see on the coast, there's the blue square is Sandy Hook, the inset square is Manhattan Island, and we can make a composite data set from all these tide gauges because the tidal attenuation in New York Harbor is not very large. So the questions that we ask today are, what are the probability of extreme events in New York City, in New York Harbor, and is there any trajectory since 1844? And to do this, I first went to the archives and took many pictures. For all the data so far, I've probably taken about 50,000 pictures of data from all over the US. And for New York, students have digitized about 500,000 data points. And there's other projects going on right now as well to digitize Charleston and so on. There's also extensive quality assurance that has to happen. I won't go into that, but just rest assured that these have been vetted. And then in terms of analysis, I come from a estuary tides background, so we do tidal analysis on the data, and we also do extreme value statistics to see what are the return periods and so on. This is some of the data that we can get. We can separate extratropical and tropical storms. We have about 200 tropical storms over 0.4 meter surge height and about 2,000 extratropicals going back to 1860. And we can look at individual events as well, and so we're starting to do that. So what do we see? What are some of the results? Well, if we take an annual maximum approach and look at the annual maximum storm tide, so that's the measured water level minus the mean sea level for that year, what we see is something like this, a composite data set in which there's natural variability, as you might expect. But if you take a close look, for example, at this dotted horizontal line, what you'll find is that there's a lot more exceedances over that line starting in about 1950 as compared to previous. So before 1950, we only know of one event that was over 1.9 meters, and after that, it's about 7. So that suggests that there's some sort of long-term secular change to storm tides in New York Harbor. And we can take this annual maximum data set and do a GEV statistical analysis and get return periods. And what we did is a 37-year moving GEV analysis and looked at the 5- and 10-year return periods. And this is in the GRL paper that we published earlier this year. And what you see if you put it together with sea level rise of 45 centimeters is that you have about a 2.5 foot or 0.7 meter increase in the storm tide, and that it's outpacing sea level rise. So something is going on in addition to sea level rise. It's not just that waters are rising and the storms are added to that. There's also some long-term process that's increasing storms. And so we can also look at this in terms of storm surge. Now, the storm surge is just a meteorological component of the storm. And there's 4 lines here. The blue lines are tropical events, so summertime or late or fall events. And then the black are extratropical events. And pre-1922, we see curves that look like this, where they flatten out. And post-1950, we see curves that look like this. So in other words, this confirms that there's a long-term change in storm surge in New York Harbor. So what's going on? Well, there's at least 2 hypotheses that I can think of. One is local, anthropogenically caused, and one would be something that's happening in the Atlantic Ocean. So the first one is what I'm going to call the VW bus hypothesis, which is basically that over time, channel deepening and loss of wetlands and have reduced the frictional drag in the estuary. And if you reduce the drag, then you're not attenuating a wave, such as a storm surge wave, as much. You've created a Porsche. The other is a storms on steroids hypothesis, basically that something in the Atlantic is causing storms to get larger, more powerful, or perhaps the timing of the storms is changing. So that would be something like this. So coming from a tidal or an estuaries background, we think about long waves, right? So tides are a long wave in which the wavelength is much larger than the depth. And there's theories that show what you might expect in a typical converging estuary when you have a tide. So if you have a tide, what you might expect is that as you have convergence, your water level, your tides will amplify. But at the same time, there's friction, and the friction will tend to decrease, and there's this balance between them that occurs. One of the interesting things to come out of this is that increasing depth has the same effect as decreasing friction. So in other words, if you increase your depth somehow by sea level rise or by dredging, it's the same as decreasing your drag on your wave. And since storm surge is also just a flavor of long wave, of shallow water wave, it stands to reason that it might be affected by some of the similar processes. So that's the hypothesis. And you may ask, well, has harbor dredging occurred on a large scale, and has it changed estuaries? Well, I think this picture shows it pretty eloquently. You went from something like this to something like this, and in fact, it's even larger now. And if you look all over the world, you'll find estuaries in Europe, in America, where tides have been amplified over time, and we think that it has to do with increasing depth. So if you were to ask, well, where is this happening in the US? Well, a poster child in the US for this is the Cape Fear estuary in North Carolina. The green line is the change in the M2 tidal constituent in Wilmington since 1930s. And you can see that since the 1930s, it's increased by about 0.2 meters. But actually, we have data that goes back to 1880s, and you can see that it was even lower then. So basically, the tidal range in Wilmington has doubled over the last 120 or so years. So does this affect storm surge? Well, we have a preliminary model in which we've created an idealized model of the tides in Wilmington using 1888 bathymetry and 1975 bathymetry, and we've calibrated it to the tides, so it actually works in terms of tides. Then we apply some parametric wind forcing, and we get something like this. So this is a little bit of a busy plot. On this side, this would be equivalent to a worst-case scenario Category 2 hurricane, and then on this side, this would be a Category 5, so absolute worst-case scenario. And the cyan is modern bathymetry, and the blue is 1800s bathymetry. And you can see that there is actually, if these results are correct, it suggests that there's more than a meter change in the storm tide height just due to changing the depth, basically. So this still needs to be validated, but this tends to suggest that this hypothesis might be correct. What about New York? Well, if we look at New York, we also see evidence of changing tides. It's about 4% since the 1920s. If you look at Sandy Hook, however, that's the coastal station, you see the same change. So maybe there's something going on the continental shelf. We don't really know. But it gets complicated when we start looking at the 1800s because, in fact, the tide constituents in New York Harbor were larger in the 1800s than they are now, and they went down to this minimum and went back up. So we don't really know what's happening, but we know that something's happening, right? There's long-term changes to the tides, and so therefore there's probably long-term changes to other long waves. The phases have also changed, so we can run tidal predictions, and we can look at the exceedances, or the top 1% of tides, and we can see that the blue line is the modern tides, and the red line would be the 19th century, and we can see that there's a longer tail now in the largest tides. In other words, your top 1% of tides are perhaps 5 centimeters larger now than they were 150 years ago. So again, that's a slight change, but it's non-negligible. And if you add a storm surge on top of that and you have nonlinear interaction, well, perhaps that can account for some of what we're seeing. So this is a busy plot, but it basically shows that there is nonlinear interaction both on the continental shelf and on between Sandy Hook and the Battery. So basically, if you take a look at this, this is the timing of storm surge relative to low hours. So a lag of 0 hours is something that's happening at low water, and a lag of -3 hours is something that's happening during the ebb, and +3 is happening during the flood. And what we see is that storm surge in New York Harbor is much more likely to occur during the ebb or the low water than it is during the flood. And that makes sense if you think about dynamics, right? If you have opposing currents, the total velocity is going to be less and the total drag is going to be less than if you have them going in the coincident direction. The other interesting thing here is if we take a look, if we compare the top and the bottom graph, is that there's a difference between Sandy Hook, so the coastal station, and the Battery, so Manhattan Island. So there's some evidence of some processes, some perturbations that are going on in the New York Harbor, but also there's things going on in the continental shelf. And this, by the way, is robust. We also see this in numerical modeling, and I encourage you to look at Philip Orton's poster this afternoon. So there's small but measurable changes to the estuary tides, and so that might be part of what's going on. But if we really want to think about it, I think we probably need to look at the continental shelf. And the continental shelf, in effect, is kind of like hourglass shape, right? It's kind of a convergent estuary. And what that means is that maybe small changes on the outer shelf get amplified as you go towards the coast. This is a hypothesis, something that we need to look at. But what we see in terms of the tides is that there's actually an unexplained annual variability in the M2 tide. It's not river flow. I've checked that. So there's some processes happening on the shelf, and perhaps if we burrow in and understand what's happening on the annual time scale, we may be able to understand what's happening on a longer time scale as well. All right, so since this is a natural hazard session, it's also interesting to ask, well, what's the return period of Hurricane Sandy? And to do that adequately, you really need to think about the 1821 event, which is a very large event, perhaps as large as Hurricane Sandy. If you look at some of the literature, there's actually a misunderstanding that has entered the literature due to a misquoting in 1831 of this original newspaper account. So basically, if you go back to the newspaper, the water rose 13 feet 4 inches relative to low water mark. If you assume that low water mark is actually a datum rather than low water, you'll get a smaller storm surge than what is in the literature, but it's still very large. And it's about 3 meters or so, give or take. And if you include this 3 meters in an extreme value analysis, actually, let me first say that we also have modeling that shows that a height of 3 meters for a storm tide is reasonable. If you include this within a GEV analysis or a GPD analysis, what you find is a return period for a Sandy event of about 300 to 500 years. This is storm tide, so that's a little bit, that's a faster return period than what has been estimated in the literature. If you don't include 1821, it's 500 to 1,000 years. And you see something similar for the storm surge. It's maybe a 200-year event if you include 1821, and a 500-year event or so if you don't include it. So that's it. But the old data I'd argue, are very powerful way of trying to quantify long-term change. We don't really know yet exactly what's happening, but we're working on it. Storm tide levels in New York Harbor have outpaced sea level rise, so I think that's an interesting thing to take into account and to try to figure out why that's happening for future projections. And we need to do more work. So thanks.